Well, looks like we can start. Welcome back, everyone. This is the last class of the 15th week that we're on, so that's pretty amazing. All we'll have left to do after today is just get through the final exam. Any questions at all to start us out today, folks? Okay, well, we started this document here after finishing our content in section, where was that? 5.2. So I guess we'll just continue to go through these problems right here. But as we're solving those, if there's some questions that you would rather see solved, they could be from anywhere. Web assigned questions, problems from old exams, problems from down here, some of this sample exam material. Don't hesitate to throw them out there. I'm very happy to just interject a problem right in the middle. But this is pretty much what we're doing today, just taking another look at all these problems from the past, giving them another try. And we left off on just taking limits. Any questions so far with where we're at? Okay, well, let's keep on going with these things. Limits are definitely challenging. I'm not going to throw too many on the real exam, but we did spend quite a lot of time just considering limits on their own. So you should expect problems like the ones that we're taking a look at. There might be a problem like this one where you just have to get through some algebra, do some simple simplifications, and you're on your way. Some of them are tricky, so investigate if you can directly substitute first. You can't on this one, you would have divided by 0. But on this one, if you can just throw in a value 1 for x and get a number, that's all you were meant to do on that problem. So that one's about continuity. This one's a little bit tricky, but another version could have gone like this one. If you saw instead a limit as x goes off to infinity of 4u to the power 5 plus 5, and let's change our denominator. Let's write out something along the lines of, let's say, 2u power 5 minus 5u squared plus 2, then this situation is a little bit different. Up here, the numerator had the highest power. Down here, the degree of the numerator is 5, and so is the degree of the denominator. That means there's a literal tie here, and you can use the steps that we used above. But if you did this, I'm just going to assume that you know about horizontal asymptotes for rational functions. The fact that the power balances means you just grab a coefficient here, a coefficient here, and it's really as easy as that. This limit comes out to 2. It's really not easy. We just have to identify that this problem will work out that way. A rational function with the same degree in the numerator, same degree in the denominator, always has this feature. If it looks like this one where the numerator wins, you're probably going to get infinity or potentially negative infinity. But any questions, folks, with those two problems there? Okay, well, let's continue running through these. Part D doesn't look too bad, but the closer you look at it, well, if you took the -5 and put it here, that would be a positive 25 minus 25. So it's one of those problems where you would divide by 0 by direct substitution. Instead, you have to do something, and the something on this one is factoring. The numerator, well, it's not nice looking to factor. A good way to get started is just factor out a 2. This will be equal to the limit as x goes to infinity of 2 times x squared plus 3x minus 10. Any level of factoring you're going to do is going to make the problem much more approachable, and greatest common factor is a good first step to make. This one also has a greatest common factor of x, so factor out x, leaving behind, and x plus 5. And actually, that's a pretty humongous hint. If you see an x plus 5 there, what you would probably want to try in your factoring is this. Limit as x goes to infinity. Still have to put in that 2. But I'm going to make the guess that this group right here by the red dot factors as x plus 5. And then x, something else. I'm just going to hope that x plus 5 is also in the numerator factorization, so we can do a cancellation. And what else do we have going on? If there's a negative sign, that there should be a minus here. And to get the 10, we should put in a 2. The product of 5 and -2 does give us the -10. 5 minus the 2 would give us the 3. So that factorization is in fact complete. That's all over x plus 5. Now we get the new cancellation. Sorry, question first.
Negative for limit to x to -5 instead of 2.
Oh, you're right. I'm not sure where I was grabbing that infinities. Thanks for spotting those. Let's fix those right away. So one thing that can plague you, as it did on me, is definitely don't have a copy error because that will cause massive havoc. This should have been a -5, and this one as well. Thanks for spotting it before we got to the very end. That would have looked weird for sure. I'll leave the error there as a tale of don't do what I did. Definitely copy down the same information limit. The next step, we have a cancellation going this way and this way, resulting in limit as x tends towards -5. Okay, we've got that part down. Well, all that's left is 2 multiplying x minus 2. This is the step where we use direct substitution, so continuity works here. Because we're going to plug -5 into this location, we drop the limit statement. It's now just 2 times -5 minus 2, or 2 times -7, resulting in a value of -14 altogether. So this one was a factorization technique, and not too bad once we make sure we're sending it to the right direction, not infinity, -5. I'll look for any kind of hints or shortcuts you can try to make work. Like, for example, if I were to try to factor this by trial and error, without first factoring out the 2, it is a little bit harder. I might not guess the right values of, say, 2x plus 10, x minus 2, or another right value of x plus 5, 2x minus 4. That's harder to get. So chip away at it. Factoring is one of the major techniques in algebra to save our lives here. Yeah.
Can I ask where the x1 is the denominator in the third?
This one right here?
Before we got that.
Oh no, I dropped a couple things on there. Thanks for spotting that one. So bad start for today. I should have had an x there, which means I needed an x right over here, which means it should have been an x on this one. Then down the line, -5 after direct substitution. So -5 as well. -5 as well. And then this one would have been a positive 14/5. I was just saying, make sure you copy everything to the next step. That was a little bit of a rough one. If this was a real final exam, and I did this one, let's say these are 5-point problems, I think I would take off 2 on this one. So thanks for spotting those errors and keeping us on track. Other questions, folks, with getting through this one? Okay, our first brand new limit of the day. This one was a little bit rough, but let's see what else we have going on. Aside from limits, there will be a question like this one, example number 3. And it'll be for a function about like this. Expect a polynomial function, nothing too wild. The major heart of example 3 is really just knowing the definition of the derivative as a limit definition. For these kinds of problems on the real final exam, we do have to use that limit definition for full credit. But keep in mind as well, you have a check on this answer. We do know that the derivative of this thing should be 4x minus 3 just by using the power rule. So that's kind of nice. It's a longer problem. It's a limit problem, but you know where you're going just by our prior techniques. If this was a 10-point question, I would think I'd give the majority, or at least half of the credit for getting through the first couple steps. So this is not half the credit, but this is a lot of credit already just to write f prime of x equals the limit as h goes to 0 of f at x plus h minus f of x all divided by h. So if this was a 10-point problem, I feel like I could probably give anywhere between 2 and 4 points just on this step right here, because that's kind of the heart of the problem, knowing that definition. The next steps are just executing it. So let's build this out slowly by calculating f at x plus h. To calculate this, we go to the original function over here, start writing it out, but put in a placeholder for x. It's 2 times something squared minus 3 times something. This is a pretty similar approach whenever we did chain rule, for example. Let me see if I can move this window just a bit. There we go. What's going inside is x plus h into both of those placeholders. And finally, from here, it's just all algebra. This will be 2 times x plus h times x plus h, just to set us up on that one, minus 3x minus 3h. On the next step, I would probably think in these terms. I want to associate the x plus h times x plus h, and then just distribute 2 into that result. So first it'll be x times x for an x squared. You can save a step if you think in these terms. This is x times h. This is h times x. They're like terms, so you get from those 2 orange arrows 2hx. Then finally, last multiplication is just h times h for h squared. So plus h squared, I forgot the squared, there it is, minus 3x minus 3h. Does that look right to folks so far? Okay, almost there. Let's distribute 2 into that group. So the f of x plus h portion is 2x squared plus 4hx plus 2h squared minus 3x minus 3h. And I think we've got it. That's our entire quantity going in right here. So back to the limit. It's now equal to the limit as h goes to 0 of this big long result. Following the substitution in blue, we'll put in 2x squared plus 4hx plus 2h squared. Then, let's see, minus 3x minus 3h. And last thing we have to put in is this quantity here, negative f of x. Let's continue to organize. If you just distribute a negative through there, you're on the right track. But just for the sake of the notes, let's write out negative f of x as negative through substitution of f of x, 2x squared minus 3x. We have to distribute that through, so that's negative 2x squared plus 3x. And that's what's going in for this portion. So minus 2x squared, positive 3x. That's one huge fraction. I'll divide by h. And now we do expect cancellations. So there's internal checks on this. The only way we're doing this correctly is if 2x squared cancels. Good news is it does. Then next, I have to double check my work here. I've been copying things weird today. Probably not enough copy. I had a negative 3h here. Should have copied to a negative 3h right there. Let me fix that right away. And I'm suspicious about the rest. Let me just double check. Okay, I think we're back on track. That negative 3x will cancel with that positive 3x. And all we have are just a few survivors. Here, here, and here. That one got corrected. All of them are being divided by h, so you're welcome to take a shortcut if you like. If this makes sense, you could say that this is now equal to the limit as h goes to 0 of 4x plus 2h minus 3. So the idea here is you take this h and divide it here, it's just gone. But now you have to divide it here, that drop the power by 1. And you have to divide into here. You're dividing into every term that's still left over. And that one turned into a negative 3. Let's take off a few of those so it doesn't look too busy. Last thing that happens is h goes to 0 right here. That's the direct substitution step. And that means we're done. We can drop the limit and say it's 4x minus 3. Double checking what we said before. Yep, we hit 4x minus 3. And that's the whole problem. Again, it's a good amount of algebra. We kind of hit the complexity by doing all this grungy work over on the right. But when you look at just the limit process, there's not too many steps to actually show. Any questions, folks, on running through this one? Okay, so that's not too bad of a problem. We just have to know to expect it. I think that's what makes this kind of question kind of hard. That's kind of why I always gotten a hint of reminding everyone during a review, this question will come back. It's a guaranteed question on the real final exam, different polynomial. Now on example 4, I had a question here that's a fun one. But this is not content we looked into. That's something called implicit differentiation. So I made a really fast edit right before class. Sorry about that. This is a more typical actual exam question that you would see along these lines of doing a tangent line. So let's do the new example 4. You can hide that one there. You can expect that there will be a tangent line equation on the real exam, but I'm not going to give you some nasty derivative to calculate. It should be something kind of routine. So there's a routine derivative to compute. And the steps for this process, whenever it says tangent line, really the very first thing you want to do is just get the derivative. I'll call this one dy dx to give Leibniz notation some love. Then just go on down the line. Any volunteers for the derivative of this one? Yeah, go ahead.
4x to the third power plus 4x minus 1.
Yep, exactly. So we've got a derivative down. Thank you for that. After doing that step, on step 2, all we're doing now is getting the slope of that tangent line. And this is the most important number right there. I give the full point 1, 2, but we need to know that it's the first coordinate that matters. The slope m is going to be the derivative of y with respect to x, evaluated when x equals 1. Well, that's a reminder that the derivative, no matter if you call it y prime, f prime, or dy dx, it's always a slope. So that's the purpose of this problem in a certain sense. Plug 1 inside this derivative, and we'll get 4 times 1 cubed plus 4 times 1 minus 1. Here are those ones. So that's just a glorified 4 plus 4 minus 1. And that means we're getting a slope of altogether 7. So we're just about there then. We're going to need this point 2. That's why it's there, because we're at the end step for this process. We're just about to build the equation. It will go y minus a y1 equals a slope m, the one we just calculated, times x minus an x1. So we've got some color coding to show the substitutions. We're just going back to this point. And you know, it doesn't hurt to just write this down sometimes. You put in x1, y1, and that's really good protection for your brain just suddenly switching things on you, which can happen if we're taking a timed 2-hour exam. So this will go y minus 2 for y1 equals the slope m, which we found to be at value 7, multiplying x minus the value 1. So we have a tangent line equation. It's pretty much just that. If you stopped here, I don't think I would be too opposed. WebAssign would have always complained he wants you to solve the function. And I did encourage you to do that, but these exams are timed, and that's the right answer. So you're okay to stop there. But it is traditional to solve for y, so let's just take those extra steps. This is going to be y minus 2 is 7x minus 7. It's a fast 2 sets of steps on this one. It could be tedious if there's fractions involved, in which case you're more than welcome to just stop on that line. But add 2 to both sides and we get 7x minus 5. And that's the end answer on this process. Any questions at all, folks, getting here? Okay, on a real exam, if this was, say, let's just say a 6-point question, I probably would consider this to be 2 points. This is the other 2 points. And right here, more like 1.5 points. That's kind of where the calculus ends, just to put in the information, right? 1.5 points right to here. So if you made any mistakes putting stuff in, well, at least I know that you knew the tangent line equation builds in like this. And the whole purpose of these kinds of problems is, again, that reminder that the derivative gives the slope. So that's the major takeaway on this kind of question. Any other questions or comments, folks, on running through this? Okay, so let's keep on going. These are not necessarily in order, but I think they are mostly. Next thing we've got here is, yeah, they're definitely out of order. This one is an application problem. We're in the section of dealing with exponential growth, exponential decay. And this is a good time to remind ourselves, you will need a calculator for this exam. It starts off by saying half-life of radium-226 is 1,590 years. A sample of radium-226 has a mass of 100 milligrams. That's an initial mass, so we might start off by saying mass at time 0, 100 milligrams. Half-life is 1,590 years, but that also gives us the decay rate. Let's color code this one. This is telling us that K, because it said half-life, it's equal to negative natural log of 2. So that element of the problem already determines the entire numerator of the K value. And the denominator is the half-life, 1,590 years. So all I've been doing is just summarizing the information already from the first line of the problem, and we pretty much conveyed it. That's the initial mass. We now have a decay rate. All we have to do to finalize this problem is give the total formula for mass at time t. First, let's write it down as an actual formula. Mass at time t is initial mass multiplying e to the power k times t. So that's not our answer, that's just organizing thoughts, but here's our next step. Mass at time t in this problem is your initial mass that we saw right here, times e to the power of k, this whole thing multiplied by t. I'll put t out in front and then k in like this. Let's just put the whole thing in blue. Well, there's also a negative sign, so I'll put a parenthesis to just put it in like this. Negative natural log 2 divided by 1590. You might put your negative right in front, but that's all stylistic choice for how you might organize. I'll just leave it in this format. So that was the K value, and this was the initial mass. So the function builds out pretty fast. We did do some problems in the homework and on web design and on quizzes that took a lot more steps than this. But on a final exam, I try to do the problems that are a little bit faster so we just get to the main ideas and not feel like we're getting bogged down by a lot of side parts on these problems. Part B is the punchline. Sure, this is really just a college algebra question, and we can find mass at, say, 2,000 years, mass at 5,000 years. But we're in a calculus course, so what we really care about is the rate at which it's decaying. So what we want is a derivative. Because it's asking for a rate, we need the rate of change of mass with respect to time t. And then we need to plug in the information for that derivative at the time of 2,000 years. The good news, though, is there's a formula for this. You don't have to go up here and calculate that derivative. It's tricky with chain rules and other weird constants to navigate with. The formula for this, it goes K times mass at time t. So that's pretty fantastic in a way. It means if we want to calculate the rate at its decaying in 2,000 years, all we've got to do is go rate of change of mass with respect to time equals our value of K multiplying mass at time 2,000 years. So let's start plugging in the information. K in this problem is negative natural log 2 divided by 1590. So we've got that portion down. Next for this one, mass at time 2,000 means we go back up to this function. We plug 2,000 exactly where you see t. So it is multiplied by 100 e to the power of 2,000 negative natural logarithm of 2 divided by 1590. And well, we're just about there. All we have to do is plug it in. Let me make one little correction here. I'm not a fan of this notation. It's better to write it out this way. The rate of change of mass with respect to time evaluated when time is 2,000 years. You don't have to write it that way, and I wouldn't take off points. I'm not that choosy a notation. But it's a good idea to put this in because it just directs us on what we're actually putting in and how we're calculating. Now, this is the worst step coming up. But I give these reminders a lot, and this is another good time for it. On a final exam, if part B was worth, say, 5 points, you've earned 4.5 points already just by putting that down on paper. If you make a mistake on the calculator, no big deal. I would identify that and say, you know the calculus. I'll just decide you made maybe a fat finger on one of these buttons because you're dealing with a timed exam. But still, if you can get it right, it'll give us an idea if we're in the right ballpark. So if I got a ridiculous answer out of this, I might think maybe something was amiss in the algebra and calculus potentially. So let's still try our best to get it down as perfectly as possible. Okay, going left to right, it's negative natural log 2 divided by 1590 times 100 e to the power of 2000 times, and let me come back up here. Desmos wants to make you leave the exponent when you go to times, so you need a parenthesis to say we're staying there. Negative natural log of 2 divided by 1590. That's really hard to read. Let me see if I can blow that up a little bit. Then just close two parentheses. And we have a negative quantity, which should make sense because we're saying this thing is decaying. We had a small sample of that, 100 milligrams. Half-life is 1,590 years. So after 2,000 years goes by, we're decaying at a rate of about 0.02 grams per year at that instance in time. That seems about right in the right ballpark. I like that it's negative and it's not too huge. But how do folks feel about this answer? Any questions on getting that so far? Looks like we're all set in class. That's awesome. How about for folks over Zoom? Should we take another look at this, or are we all getting about the same value? Sounds like we're okay, so let's just drop this in. Let's see. I usually put a little bit more information on what to round to on a real exam, but if I forget, just use your best judgment. I'll probably carry in at least 3 significant digits and call it negative 0.0182. And then I would probably double check if I got those digits right. Let me take another look. Negative 0.0182, looks like it's pretty good. But for the units on these, we go up to the numerator of Leibniz notation. Mass was in units of milligrams, so this is milligrams per, I'll just use a fraction for the per. Go down to the denominator, time was in years, so milligrams per year. So I'm not quite sure what radium-226 is for. Let's see if we can figure that out. I learned the other day that in Microsoft Word, if you highlight, right-click, and go search, it pulls from the internet. I don't know if this is a Wikipedia page, but that's kind of a cool way to do really fast research. It says 226 has a half-life of 1,600 years. Oh, they rounded, so that's not too worrying. It's the most stable nuclide. Well, we'd have to dig in a little bit further. Probably something in medical sciences is what I'd imagine. But any questions at all, folks, on running through this one? Okay, it's been a while since we've seen this problem, so watch out for part B. I think that's the hardest thing about this because when it says rate, it's an indication that you're really using that formula, which can be easy to miss on this kind of problem. But let's go down and see what we have up next. Just a whole bunch of differentiation problems, it looks like. Let's maybe throw in a couple extra ones as well as we go through this list. I pretty much just grabbed a bunch of random things that we ought to try. So it looks like I have sum and difference rule, a product rule, a quotient rule, and something nasty with logarithms. I'm not going to go too crazy on logarithms, but any practice we can get on these is always good practice. So we'll try out this harder problem as well. First off, there's a big problem with this function. You would never ever want to differentiate it in this format because that is never considered a quotient rule type problem. That's making a mountain out of an anthill in this situation. What you really want to do in this problem is fix it. And by fixing it, what I mean is put these things algebraically in just a better form. You could take this thing and write it as -3 times x to the power of -4. Now that's way easier to differentiate. I can't do anything with 9 natural log x, so we'll just put that in. This is an even trickier problem, -5 power x plus natural log 6. So really all I've done here is corrected that exponent down there. Now, next thing, I'm noticing we have some nasty derivatives ahead of us, so let's put down some formulas to organize. If this derivative comes up, it's not so bad. Natural log x prime is 1 over x, but watch out for this one. This is the not so nice one. If it's log base b of x prime, we get 1 over x times the natural log of whatever that base was, b. That's an easy formula to miss. And the reason to write out these is, well, the natural log occurred, but also something even nastier occurred. 5 to the power of x is not an easy derivative either. Think of it in these terms. If it was e to the x, everyone's happy because that derivative is just itself. But if it's a base b to the x, much like the logarithm one, the derivative of this one starts out first by copying this pattern. It becomes b to the power of x. But then we need a corrective factor. We multiply by the natural logarithm of b. And notice the pattern on this one. It's a base b exponential, you're multiplying by natural log b. If it's a base b logarithm, x still goes down, but then it's multiplied by the natural logarithm of b. So that's a common feature to both of those formulas. Now at this stage, we can differentiate and say f prime of x equals, down the line, -4 by 3 will give us a positive 12, x to the power of -5. This one is going to turn into 9 over x. So the constant is completely unaffected. All we're doing is dropping x to the denominator. But now let's be really careful with this one right here. Any volunteers for what the answer should be from that portion? Really close. It would just be a 5 for that natural log. Absolutely. It's really tricky because that negative is actually a constant multiple rule of -1 times 5x. That's what makes it just extra tricky, more tricky than it even looked like. So that -1 stays right where it is. Then derivative of 5 power of x is just visualizing it this way. 5 goes here, here, and here, and that's our process. 5 to the power of x times the natural log of 5, and we're on our way with that one. I think this portion right here is the trickiest part of the entire derivative, so watch out for those kinds of things. These formulas don't come up a lot, but when they come up, they are not easy to use. We have to be pretty careful with them. Okay, so we're on our way. Next thing we have the natural logarithm of 6, but that thing is a constant. Its derivative would go to 0 immediately, which means you can just leave your answer just like that. We now have the full derivative. Any questions at all, folks, on this answer here? Okay, so that's one derivative down. Next one is worse, and let's see here. It's not terrible, though. We just have to anticipate what's going on. If it looked like this, that's a nice derivative. The derivative of that thing is just 18 e to the power of x. But the moment you put an x back, now it's a bona fide product rule just right out of the gate. So let's analyze this one carefully. I'll think of blue as the first factor. Green is going to be the second factor. And now g prime of x should be analyzed in this way. Just like we did with function notation on the problem where we're taking the derivative of the limit and we put in the placeholders to put the x plus h in, same idea works really well for both product rule, quotient rule. So if you're finding these kind of hard to analyze, you don't have to take all the shortcuts that I would have taken. You could just do it like this. There'll be plenty of the time on the exam to analyze these really carefully. Things to watch out for is make sure you put the derivative symbol here and here. It really does matter. If you didn't put it on, you are much more likely to forget to actually differentiate these things. And also, if it's a product rule, we'll use plus. Then here's the pattern. Just put in 18x cubed into the first placeholders on both terms. E to the x goes into the remaining placeholders. And at this stage, we're basically done. We just have two nice derivatives to run through. Well, they looked nice, but that's a 30 plus 24, looks like a 54. Don't forget your calculator on the exam. Sometimes the numbers are a little bit not so friendly. I should get a 54x squared on that one, multiplying e to the x. I'll still use the color coding just to signify those were the things we differentiated. So this one's copied in, plus, copy in this one, 18x cubed. Derivative of e to the x becomes itself, and I'll put it in green to signify, yes, we differentiated it, but nothing happened. Then that's where the whole problem ends. You don't have to do anything further like factoring, although it wouldn't hurt if you wanted to, but it's just extra steps you didn't have to take. But if we were looking for a critical number, yes, you would factor this, set it to 0 and solve. But that's one product rule down. Any questions at all, folks, on this one? Okay, so after product rule, I think the most logical derivative to do just immediately has got to be a quotient rule. And so there it is. I'm noticing on this list, we're missing a chain rule. So I'll brainstorm while we're solving some and just put a reminder for part E. Let's do a chain rule as well. There's a chain rule built in here, but I want a more direct chain rule just for the sake of a good review for us. So now on this one thing to keep in mind is if you had a function that went like this one, y equals 5v minus 3 over v, this one is not the quotient rule. This one's a freebie. What you would do is write out y equals 5v over v minus 3 over v. This is 5 minus 3 to v power -1. So I did a cancellation on this first one, brought this exponent up into the numerator like this way, and now suddenly it's not product rule, it's not quotient rule, it's just a sum and difference rule. So y prime in this land will give us a 0 here, then a positive 3, v to the power of -2. So watch out for these kinds of exercises. There may be some problems on the final exam where you can make this a big problem with a quotient rule. But if you look at it really carefully, you really didn't have to. So try to find some shortcuts. It doesn't work on this one, unfortunately, because if I divide 5v by e to the 5v, there's no reduction in complexity there. It's just as complicated. You could also go 5v times e to the power -5v. But all I've done is exchanged a quotient rule for a product rule that are just as hard in either format. So this is a problem that's best suited just to directly hit it with the quotient rule. I'll think of that as the top function. This is the bottom function. And let's hit it with y prime by just analyzing the pattern. Here's the pattern if it's a quotient rule. It feels a lot more built up, but it's not too different. Don't forget your primes like before that we did in the product rule. This is a mistake that I'm most in danger of making personally, so I try to always make a big deal of that negative sign. And don't forget to put a power 2 there. Now there's, 5 positions to throw stuff in, so it feels like it's kind of overwhelming, but there are patterns. Just like with the product rule, I took the first factor and put it into the first slots. The quotient rule, take the top function, it'll go here and here. And that's the only thing that happens with the top function each and every time. So if you memorize that one aspect, then you will now know e to the 5v just goes everywhere else. So it's here, here, and here. We still have to crank out the last 2 derivatives and simplify as much as is reasonable, we should also say. But once you get to here, the problem is mostly done. Any questions at all so far? Okay, let's see what it actually ends up then. Now, in the numerator, going left to right, the derivative here is just going to be a 5, which is multiplied by e to the power 5b minus 5b minus 3, which is multiplied by this derivative. Now, suddenly we need to be careful right here. We're going to do a new chain rule problem, but within these problems, smaller chain rule processes can sometimes creep up. Let's do this one carefully, just on the margin to help us out. If you're analyzing this function, y equals e to the power of 5b, then here's what the chain rule process looks like in this scenario. Y prime will be equal to e to a power multiplied by the derivative of that power. So that's the setup for chain rule every time it's an exponential. Next, the inner function will go into both locations, here and here. So on the next page, we'll have that y prime is equal to 5. That's a derivative from right here. I think it just looks nicer up in front, so I moved it up in front, times e to the power 5b. So back up here, following this work, it just tells us that that is, 5 e to the power 5b. All of which is now divided by, new thing we can do is, in exponent laws, this 2 will multiply 5b, so it's really e to the power of 10b, but you might decide, do we need to do that? I want to actually just leave it in this form, e to the 5b to power 2. Because in simplifying this one, there's actually a pretty big cancellation that goes on. E to the power 5b here and here can be factored out and canceled with the 2 power or 2 factors we see here due to the power 2. But on a problem like this one, let's say it's out of 5 points, getting to here is either 4 or 4.5 points. We still have to simplify them, but this is now just algebra. It helps us out though, because if we were looking for a critical number, we needed to do that algebra. So let's take an additional step to simplify. We'll have to use the continuous arrow. Y prime is now equal to, let's factor out 5 e to the 5b. That will cancel right here, leaving just a 1, minus, cancels all of this right here, leaving just a negative 5b minus 3. Then down below, e to the 5b to power 2 now gives us this pretty massive cancellation for a problem like this. E to the power 5b has canceled. This is now just to a power 1, is how I visualize that cancellation. Does that make sense to folks on how it's been visualized with those slash marks? Okay, so all that's left is the factor 5 outside. I need to do some distribution. That's one downside of simplifying, is sometimes you get all these additional steps you didn't expect. It'll be a 1, distribute the negative inside that group, minus 5b plus 3, e to the power 5b. And here's finally our answer. I think I need to go down. I'm running out of horizontal space. This one ends up at 5, 4 minus 5b over e to the power 5b, finally, after a good amount of steps. I think this one is a pretty tricky quotient rule to get through. But if you got to this stage, you're doing all the calculus really well. So that's the bigger takeaway. Any questions, folks, on the conclusions here? Okay, so those are the product rule, quotient rules. Next, let's give this one a try. What part D really is a big review on properties of logarithms. But those properties of logarithms become properties of calculus in a certain sense. That sense is that if you try to do this problem directly, it starts out as a chain rule, then a quotient rule, with a product rule, with another chain rule. We could be here all night trying to solve this one and doing a lot of backtracking. But properties of logarithms make the derivative almost immediate. It's kind of impressive. So let's start off by saying, first property we're going to use is the one that breaks up the quotient. It's natural log A over B is just the same as the natural logarithm of A minus the natural logarithm of B. So that's our step one. That means h of t, we can't put the prime on because we're not differentiating it yet. We're just using algebra to re-express it. Will be equal to natural log x e to the power of 10x minus the natural log of the square root of 2x minus 11. So that's our first step in expanding this out. Now we still want to do a couple more things. Right here, that's a product of two functions, and so now we can use the product rule of logarithms. So that would be the rule that goes natural log of a times b equals the natural logarithm of a plus the natural logarithm of b. So we'll use that in a moment. But I did want to highlight one kind of cool thing about properties of logarithms, as well as, say, the quotient rule. If you see a quotient, you're putting a negative in, and that might remind you of the negative in here from the quotient property of logarithms. Likewise, with the product rule, you're using a plus, and that reminds me of the plus right here in the product rule for logarithms. So that kind of inconsistency in mathematics is not always guaranteed, but it's nice when it happens. Helps with memorization a whole lot. So now by the red dot, I'm going to use the second property that we wrote down. And it's still h of t. Now it's equal to the natural log of x plus the natural log of e to the power 10x plus, oh, not quite plus, let me try again, minus, copy errors are a terrible way to lose points, minus the natural logarithm of, some folks might have a good suggestion to rewrite this. What would be that real power on that symbol there that folks are looking at? Any volunteers over Zoom for what that power should be for that square root?
1/2.
Absolutely, thank you, Ashley. So this is 2x minus 11 to the power of 1/2. And now that we've exhibited that power, we can do something with these things. This power is going to come down, but you might visualize it also a little bit differently. It goes like this. Natural log of e to the x is just x. There's always a cancellation that way. If it's a different logarithm, log base b of b to the power of x is also x. So those two properties convey that that is just a 10x we're looking at. And the next property is the reason for exhibiting the exponent is because we can say that the natural log of a to the power p is p times the natural logarithm of a. So that 1/2 is just going to move up in front on our next line. Still, it's not the derivative. We're still just looking at the original function h. But now it's as convenient as possible for differentiation. It goes natural log x plus 10x. Over here, this 1/2 is going to come down, so minus 1/2 of the natural log of 2x minus 11. So that's the function that we're going to differentiate. This one is just a formula for the derivative of a logarithm. This one is a constant multiple rule, but that one's a chain rule. We'll be careful on that one right there. So now we're doing the derivative. We could call it h prime of t. Now down the line, this is a 1 over x in a derivative. Derivative of 10x is just 10. And I'll copy the constant because we're using the constant multiple rule. Negative 1/2 multiplying. And now let's be careful on this one. We've done a lot of chain rules, but we haven't done the most chain rules when it comes to natural logarithms or any logarithm. So let's pause right here. The inner function is the thing going inside. So usually that's the first thing you'd want to spot. This is function 2, inner. That means the natural logarithm itself is function 1. That's the outer function. So the pattern on differentiation is, if it was natural log x, you just throw x into the denominator. If it's natural logarithm of a bunch of stuff, take all of that stuff, put it into the denominator. We're going to multiply by the derivative of that stuff, so you can either put it right here if you like, or just throw it up into the numerator. I'd say that's entirely up to you. Don't forget the prime symbol in the numerator because there is still one extra step. Now, take your inner function and copy it into both of those open placeholders. 2x minus 11 goes here, and here as well. So we're nearly done, folks. We just need to resolve this last derivative. The whole answer turns into 1 over x plus 10 minus 1/2 multiplying. The denominator can't change, so just 2x minus 11. But the derivative of this numerator becomes a 2. And that means there's more steps. We get to simplify it because the 1/2 here can cancel the 2 up here. So here's the cancellation. Leaves behind a 1, and so now we have 1 over x plus 10 minus 1 over 2x minus 11. So that was a pretty tough problem. We saw something like this on exam 3, but I'm not going to go for double jeopardy. We did this one again, mainly for the sake of just additional practice. There will be logarithms and that kind of stuff that you'll see on the exam, but nothing as built up as this one. Still, if you're studying for a final exam, you don't want to study problems that are as hard or easier. That's a disservice. You want to study problems that are as hard or harder if you're studying for a final exam. That's what's going to really help out. But any questions at all, folks, on part D? Okay, we have one more before we switch gears. So let's do one good chain rule. Everything that we did chain rule wise was just a sub feature of the problem. It wasn't the main thing. So for a problem where the chain rule is the main element, it could be something like this. F of x equals 1 over the 11th root, which just seems pretty arbitrary, but you can define an 11th root. So here it is, of 9x plus 12 to the 3rd power. So in my mind, this is a really good chain rule problem, but it's also a tricky one because we wouldn't want to attack it with the chain rule directly. We first have to do a little bit of algebra just to express it the right way. Excuse me. So my first step on this one is to fix this expression right here. There's a really good trick. If you have an 11th power, it will turn into an exponent, but it becomes a denominator in that exponent. So this all turns into 1 over 9x plus 12. It was to the 3rd power, but now it's being divided by 11. So if you're getting back into exponential format, this is what would happen to that index. Any questions to that step? I feel like that's a tricky step already on its own. Okay, I think it's a good time to step back and appreciate, if you really want to learn algebra well, take a calculus class because you're going to learn some of the weirdest algebra you've probably never seen. Stuff like this comes up all the time in a calculus setting. And we have to deal with exponents even more. We want to call this 9x to the power of 12 to the power, whatever it is, flip the sign. If that was a negative 3/11, I would have written it as a positive, but it's already positive, so it comes in as a negative 3/11. So we didn't do any calculus at the moment. That's just algebra, try to get it into a format where calculus becomes manageable. So now that we're here, we can analyze this better. The inner function is the thing going inside, much like it was up here for the natural logarithm. So again, inner functions are the easier one to spot. This exponent here is an outer function. What was the function? It'd be something along these lines. X to the power of negative 3/11. It just so happened that where x is, someone put in 9x plus 12, and now it's a harder problem out of nowhere. But we're about done. The derivative of this will go like this. F prime of x equals. Now, the first thing we want to deal with is the outer function. As the order 1 and 2 is indicating, we need to deal with that first. But when you differentiate these functions, the power comes down. So here's negative 3/11. The new power is going to be this minus 1, which is just a fancy way to say take negative 3/11. Subtract an 11 elevenths, that's taking away one, to get negative 14 elevenths. That's our new exponent. Kind of annoying, but you know, it's good practice. Negative 14 elevenths. So all I've done is the derivative of the outer function. That came down, power is one less, but you always want a placeholder for what is going inside. Then multiply it by a derivative like that. This was the inner function. All that happens next is we just throw it right inside. 9x plus 12 here, where it's complete, and 9x plus 12 here, where we still have to differentiate. So one last step. So finally, derivative of this one is nothing but a 9. That 9 is going to multiply the negative 3. So the end answer is negative 27 elevenths, 9x plus 12 to the power of negative 14 elevenths. And some people in this class might drop this down to the denominator, making it positive. You might express it as a root again, an 11th root. But I would encourage you to be satisfied with that answer. You can do additional algebra, but I'm always completely fine at this step. You already did some interesting algebra just to get it into that format here. Any last questions, folks, with that new chain rule problem here? Okay, we've got about 19-ish minutes, 18 minutes and some change. So let's start cherry picking these a little bit better. I just wanted to make sure we got through a lot of good derivative practice because that helps everywhere on the final, almost. So I'll leave it up to the class. I did X this one out. We didn't make it this far to the course to do these kinds of problems. We got awfully close, unfortunately. We do have a problem on pharmacokinetics. So here's the application one. We have a tricky one on minimums, maximums, and concavity, and some applied problem on finding antiderivatives. Oh, and I should say, oh no, this would be a one that we did do in section 5.2, right at the end before we said this is the end of the material. So out of all these questions, I think they're all pretty good. I will be solving all of these, by the way, and posting the solutions so you can come back to them. But I'll leave it up to the class. Any volunteers for choosing the next direction to go? Yeah, go ahead. Good call. This one is pretty tricky. Let's give concavity a call or a try. This will probably be our last question for the day, but again, I am going to come back to all these and give the solutions. These kinds of detailed solutions as well. So concavity, we've got a logarithm, so this is a good review problem. We're going to hit a lot of different stuff throughout the course. First thing we want is the local maximum, local minimum values. That means we have to differentiate once and find the critical number. So first step is f prime of x. Now this one's a logarithm, which means the formula always goes like this. So that's our chain rule analysis. Sometimes I take this whole group with a prime and put it up into the numerator, but I'll always leave that up to your call. It's sometimes a good shortcut, but it can make the pattern a little bit vague on how you're doing the chain rule. Next thing you do is you grab the inner function, x power 4 plus 27. It'll go here and here. Now, when I differentiate this, this is just going to be an x cubed, and I will just multiply it up into that numerator. 1 times x cubed just gives the x cubed. It's divided by x power 4 plus 27. And the first derivative is not too bad, but notice we also want concavity. So we are going to have to differentiate that again, and it's going to be a quotient rule next. However, for the moment, we are setting this equal to 0 because we're looking for critical numbers. Yeah, go ahead. Oh, yeah, absolutely. Thanks for spotting that one. That's a bad way to lose points on these kinds of things. Another look on it, just for my sake. The 4 comes down and becomes a coefficient, and then the new power is 3. Thanks for spotting that one. Other questions at the moment? Okay, now solving this equation, it just boils down to 4x cubed, the numerator, set to 0, and there's only one solution. X equals 0 is the critical number of f. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 + 2 × 2 = 4. 1 Once we have that, if we're looking for minimums and maximums, we still have to do a little bit more work on this. We need to analyze the entire real number line, going from negative infinity to positive infinity. Drop the critical number somewhere. And next thing we do is test intervals. Let's see, what's a good pen for that? Let's go with purple. So there's a infinitely long region here, another region of infinite length going here. This has no context, so negative values are just fine. That means -1 is a good choice, +1 is a good choice. We're plugging all that right here, the first derivative. The denominator is always positive, so this can sometimes be a pretty quick process, but just showing the paper trail in the notes, here's what it looks like. -1 plugged in would give us 4. -1 cubed. Divide by -1 to the power 4 is just 1 plus 27. But that's negative because of this portion right here. So it's -4 divided by 28 altogether. But the most important fact is that the derivative is always negative now as you go to the left of 0. I'm expecting positive to go on the right, but let's double check. Oh, one mistake I should be very cautious of is that should be a prime. Oh, sorry, question first.
To clarify, where did we get the -1?
Oh, that's a good question. Once we got the critical number of 0 right here, we had to partition the real number line like this, but then it's completely up to your choice. This is one of those weird things in mathematics where any number to the left of 0 would have worked. Some folks might have picked, say, -2, -3. I just decided -1 is the easiest one to plug in. And same idea going to the right. If this is your critical number, anything to the right of 0 is going to work. 0.001, in fact, would work for us. But be kind to yourself. Use an easy number to test, like +1, and you're not working too hard for something that shouldn't be too big of a deal. But what is a big deal is, forgot the prime symbol on that one. You definitely want to remind yourself you're testing f prime at -1, f prime at +1, because it will remind you to come back to here, plug it into that function. But if that's a +1, this is just a 4 times 1, 1 plus 27, so this is 4/28, definitely positive. This then conveys, by the first derivative increasing decreasing test, that on this interval, the whole function is decreasing, only because we said the derivative is negative. Here the derivative is positive, that means the function is increasing. We don't necessarily have to say where it's increasing, decreasing, because the problem is just asking for local maximum, local minimum values. Well, we have only one critical number, so we only have one extreme value, and we can now say that f, throw in that critical number again at 0, equals, but here's why I try to be really careful with the symbolism. F primes here was important to get this down right. And now it's really important to call this just f, because you're going back up to the original function to find what's going to be at the local minimum. So this is going to be natural logarithm, 0 power 4 plus 27, which means it's the natural logarithm of 27, which is a local. I'll leave this one up to the class. Would you call this a minimum or a maximum?
Minimum.
Turns out it is a minimum. Good call. And here's a way to visualize it. You don't have to do this on your paper, but I've actually done this a lot on real situations as a real student taking an exam. If you say it's decreasing, then the graph to the left here must have looked like this. This was a critical number, so it had to have a horizontal tangent line. That's when the derivative was 0. But then over here, it said it's increasing. And this much is a lot to help us out to get the right determination. Pictures are everything sometimes because math is abstract enough. If you draw a picture of what's going on, you're making it slightly more concrete. And that's giving you a tremendous upper hand in a lot of contexts. So we'll say this is a local minimum. You know what? Let's leave that on paper just to convey that's not a bad way to think about these problems to help out. Well, any questions, folks, on finding the local minimum? Okay, there is no local maximum, but you don't really have to make a statement on that. If you did, I'd say you're being really careful. That's great analysis. If you didn't, I would just assume you're on a timed exam, so you're just trying to get to the main things. So let's do that here. We don't have to convey that there's not a local maximum. We'll just imply it by not saying anything further. But what do we need to do next? We're looking into concavity, which means we need to take these functions right here. Let's add a little bit more to the instructions. On what intervals is f concave up, concave down? And let's add here also, what is the inflection point? Just in case that's also asked. We'll put it in red just to show it's also an edit. Here's the screenshot of the prior information. And now to take on concavity, what we do immediately is go up to the second derivative now. This was a nasty one though. The second derivative is not as friendly as it could have been. It's another quotient rule, but you know, that's just as well. This is a final exam review, so we're reviewing quotient rule in the middle of concavity. So f double prime at x, first being careful, goes like this. Okay, so that's our quotient rule setup. I'm thinking we're going to need a new page, so we might as well get on track for that right away. Next, the pattern is take your top function, you plug it into these two positions, you're all set up, because now x power 4 plus 27 has nowhere else to go, and these are the right places to plug them in. Actually, not too happy with the penmanship on this. One thing you ought to be really careful about, I'm not super picky, but sometimes this can actually come back to haunt us, is definitely try to make your exponent really look like an exponent. If it gets a little bit vague, other instructors might get picky and mark you off for that by not making it look absolutely like an exponent. But let's keep on going through this. This derivative is nice. This will be a 12x squared multiplying x power 4 plus 27 minus 4x cubed. This one is another nice derivative. This will be times 4 x power 3. And the whole thing is divided by x power 4 plus 27 squared. Okay, so we're just about there, but this is the steps where actually simplifying your functions after quotient rule pays off, because now you've got to do it. There's no choice. I need to set that equal to 0 and solve, but solving in this format is just an exercise in working really hard when you don't have to. I'm not sure what that statement was going to be. So first we distribute. Here to here is going to be 12 x to the power of 6. Next, I'll need a calculator for this portion. I need 12 by 27. So 324 for that portion. And it has an x power 2 as well. So that finalizes the distributions. This one's not a distributive law. We're just multiplying -4 times 4 for a -16. X cubed times x cubed causes the powers to add up. Now it's x power 6. All which is divided by x power 4 plus 27 squared. I don't know why, but these numbers are starting to look kind of familiar. We might have solved this problem before, but still it's a pretty good problem. Next, we're combining like terms. So I'll take the 324 first. Then it's 12x power 6 minus 16 of them for a -4 x power 6. Denominator, you'll notice we always leave it in its factored format. There's almost never any value in expanding this out. So just x power 4 plus 27 squared. Now, finally, our next steps are just to factor this as much as possible. So I believe 4 goes into 324, and I have a strong case of deja vu. We might have done this problem, but I can't quite recall. 324 divided by 4 is 81. So let's factor out 4x squared. The 4 divides here, leaving an 81. X squared is eliminated. Here, we factored out a -4, so we have, excuse me, a +4, so we just have a negative sign, and an x power 4 left over. All of which is divided by x power 4 plus 27 squared. And at this stage, you could continue to factor this out if you'd like, or if you wanted to, you could set it equal to 0 and solve right away. In fact, let's keep on factoring. It might be kind of valuable to show those last steps. 4x squared. This is a difference of squares, so it becomes 9 minus x squared. Multiplying 9 plus x squared. This problem seems to keep on going. I want to be upfront though. This is a good problem for practice, great for getting really good practice on the final exam. But I wouldn't ask a real final exam question this long. This one's turning into kind of a slog. But again, that means it's definitely good practice. This portion factors further, so we have 4x squared, 3 minus x times 3 plus x, multiplying 9 plus x squared, all divided by x power 4 plus 27 squared. This is as far as we can factor. That's a sum of squares, so it doesn't factor any further. That means we can set it equal to 0 and solve right at this step. And the whole reason for all the factoring is the only possible way that this is really equal to 0 is if the numerator is 0. So this will imply 4x squared is 0, or 3 minus x is 0, or 3 plus x is 0, but not this one. This one set equal to 0 has no solution that's a real number, so it's just down to these 3 equations. So this implies x equals 0. From this one, it'll be a +3, and from the last equation down here, it'll be a -3. So those are the critical numbers of f prime. And now with all that work, we get to do the fun step of analyze the real number line. We first have to make the cuts of 0, -3, +3, and we need to check 3 different intervals. Let's see, I'm running a little bit shy on time, but let's see how far we can get on this thing. On maybe this interval right here, I would use a test value of a 1. Well, let me try again. -1 is the actual value there. This interval, I do use a +1. -4 here, +4 here. So those would be my test values. And they're all going into this right here. Let me see if I can zoom out just enough. There it is. So this is the second derivative carrying down those equalities. If we put a -4 in first, we're going to get f double prime -4 equals 4. -4 squared. Over here, this is going to be a +7. This will be a -1. This is just positive, but let's put it in. That's 16 plus 9, so a 25. Down below, that's absolutely positive for several reasons. That's -4 to the 4th power plus 27 squared again. And that tells us, well, let's take a look. That's a +16, positive. There's one negative sign right there that survives. So the whole thing is negative. So right over here, f double prime is less than 0. And because we're short on time, let's take a shortcut next. I'm going to finish out these notes and show the rest of the test values, but let's use multiplicities to analyze the rest. At -3, that came from this one, which is to a power of 1, which is odd, so our sign should flip. At 0, this came from the power 2 from x squared, which is even, so the sign stays the same due to that even multiplicity. But again, if I had time, I would definitely test this out just to make sure I didn't make any silly mistakes. Right here at 3, that came from this one. Power here is 1, which is odd, so the sign changes again. And here's the summary of why we did all this. This region is concave down. because the second derivative is negative. Here it's going to be concave up, then concave up again. And then finally, oh, hang on. Concave down. And then I think I have a mistake here. I should have flipped my sign on this one. That's why this is a dangerous step. To bigger than 0, which means this one should have stayed bigger than 0. And it's this one that should have gone negative. So that shortcut is dangerous. It's a little bit of a tricky analysis. This is concave up, and then concave down. Our end answer is going to be intervals like this. F is concave down on, let's take a look, from negative infinity to -3. Union, again, from 3 to infinity. I need to make another statement for when it's concave up, and then find the inflection point, but I definitely over time. Sorry for stealing a minute of your valuable time. But I'll come back to these notes, finish out what we did here. It looks like there's an inflection point on this one, because concavity changed, and on this one. So the last thing you have to do in your answer is just put the -3 inside this function to get -3, f at -3 for one inflection, and again with that point there. But this is not a change in concavity, so that one is not an inflection point. But any last questions, folks, with the end of the work here? Let me put a answer or a reminder for me. Okay, so this is more for me, so I don't scroll through the problem thinking it's finished. But I think this is a good stopping point for us, folks. If you do have questions over the weekend while you're studying, please don't hesitate to reach out. I'll definitely get back to you. I always check my emails in the morning, but feel free to email me at any time, even if you're up at 3 a.m. for any reason. You're welcome to send out that email. But otherwise, have a relaxing weekend, folks. Our final exam is for the in-person section going to be, let's see here, Monday, April 29th in this classroom from 8 p.m. to 10 p.m. And standing offer for the in-person section, I'm also giving another final exam on Tuesday, April 30th from 5:30 to 7:30. If that's an easier time to you, just send me an email and I'll make sure I have an exam ready for you. Otherwise, for everyone else, it's going to be the Pocatello Testing Center whenever they can accommodate you. Any last questions, folks, at the moment? Okay, well, have a great night, everybody. Sorry for stealing quite a lot of your time this time, a few minutes. I think our balance is pretty close to 0. But we'll come back for the final exam and then we'll be done for the course. So congratulations on getting through it all.
Thank you.
You bet. Have a good one.
Just a quick clarification on the inflection points. Is that for plugging in those values, you plug that into the original f of x equation, not the second derivative?
Exactly. It's got to go into that original function right here.
Okay, perfect. I think I always screw that up, so.
Tricky. There's like 3 functions on the table when you do these. So yeah, it's a easy one I meant to do.
Awesome. Thank you.
Yep. Have a good one.